Thank you, Shugwang. So hello, everyone. I'm going to talk about some recent works and also less recent works about how to include spin degrees of freedom in hydrodynamics and how to construct somehow what we now call spin hydrodynamics. This talk is mainly based on these two papers, which wrote in collaboration with Nora Weigenand, Xinli Sheng, Chun Wang, and Dirk. So, okay, I'm now employed at the University of Illinois at Urbana-Champaign, even though remotely, because no visa and COVID reason, and so I'm based here in Frankfurt. This is just description. Okay. So this is basically the outline of my talk. So we are all interested in describing spin physics in heavy ion collisions. And here I will focus mainly in I will mainly discuss how to include spin degrees of freedom in three sort of fields. First, we'll discuss thermodynamics, then kinetic theory, and then eventually we will go to hydrodynamics, which is somehow our goal. First of all, something about something about the non-relativistic physics. In condensed matter, there is an effect called Barnett effect, which is when you get a ferromagnet and then you start to rotate it, so then you will observe a magnetization along the rotation axis. So this connects the notion of rotation with the notion of polarization, and this is some very sort of fundamental example in relativistic physics in which you have the connection between a macroscopic quantity, namely the rotation of the ferromagnet, with something that is in principle a quantum feature, so the polarization, so something microscopic. And so what we will see is whether something like this, so some polarization effect induced by rotation, can also happen in relativistic systems, and especially in heavy ion collisions. And the answer is yes, because as we know, in non-central heavy ion collisions, the large global angular momentum present due to a finite interparameter of the two ions can generate a vorticity in the quark-gluon plasma and in general in the hot and dense matter, and this will in turn generates a particle polarization along the vorticity. This is somehow what one would expect, and this is actually what was being observed. We all know about this very important experimental observation of the lambda polarization, studied through the Wick decay of the lambda particles, and it was such an important discovery because it could have been possible. It was possible to estimate the vorticity of the quark-gluon plasma based on thermal models, and it turned out that is by far the most vortical fluid ever observed. So now the question is that there is this discrepancy now between experiments and theory known as the sign problem, and here I would go quickly through this. So we can project the polarization vector of the lambda along some direction that in principle we can decide. So if we project the polarization of the lambda along the global angular momentum, we have this famous global polarization, but we also can choose to project the polarization vector of the lambda along the beam axis and make a more differential analysis, so study how this polarization varies as a function of the azimuthal angle in the transverse plane. And we see a pattern which goes as a sine function. And we see the difference between sign between the experimental observation here and the theoretical prediction here and the experimental observation here. All these models used to calculate such theoretical predictions that were able to describe so well the data of global polarization or observable of lambda polarization. Somehow they fail in describing the longitudinal polarization because of this sign difference, difference in sign. And so now people started to sort of bring this new idea in the field of whether one should relax the hypothesis of equilibrium of spin degrees of freedom. So whether now I would phrase it in the way whether spin plays a dynamical role. So we know that relativistic hydrodynamics is a very good effective theory and for the heavy ion collisions. And the problem of relativistic hydrodynamics when we think it as a theory of conservation laws is that in principle is a classical theory. So, and the problem now is whether how we can include spin degrees of freedom. So how can we include quantum effects in a classical relativistic hydrodynamics? So of course, the starting point, the natural starting point is to start from a quantum field theoretical definition of, quantum field theory. And as we will see, our strategy is to start from the Wigner function formalism, but we will get to there. And then to construct the hydrodynamics from quantum field theory such that it will include automatically quantum effects. So there are also other approaches, like approaches based on the entropy current analysis, and somehow one would like to find harmony with all these approaches. And this is basically what we are trying to understand. I would like to summarize our results of our recent works in these two sentences, basically. So our point is we want to be able to describe the orbital-to-spin angular momentum conversion, and what will trigger in the kinetic theory this orbital-to-spin angular momentum conversion is no locality of particle scattering in a kinetic theory. So it means that particles now will collide with a finite impulse parameter. And this will have the consequence in hydrodynamics, according to our scheme, that an antisymmetric part of the energy momentum tensor arises and will be strictly connected to the non-locality of the particle scattering. So first of all, something about what sort of inspired us. And this is pioneering work about non-relativistic kinetic theory for particle with spin, and by Hess and Waldman. And the moral in this paper is that they are not able to describe the Barnett effect from a microscopic point of view because they miss the non-locality of the collision. And they put something by hand in order to mimic such dynamics. Here, so now we would like to follow sort of the same logic in the relativistic case, although some caution must be taken, because the non-relativistic Barnett effect means that we have some magnetization different from zero. In the heavy ion collisions, what we saw in let's say in a relativistic system, what we observe is a spin polarization without magnetization, because in this case, we also have antiparticles, and the rotation will align the spin of the particles and the spin of the antiparticle in the same direction. This means that we can have polarization without magnetization. Anyways, so in the relativistic case, we need to introduce an object that would somehow allow us to describe the spin density. And this object is what we call spin tensor.
Enrico, can I ask a question? Sorry.
Yes.
Yeah, about the Barnett effect. Do you need an antisymmetric part of the energy momentum tensor to produce Barnett effect?
So
can't it be just coming from vorticity, for example?
In this paper here, they refer to something that I will discuss actually in the very end as the theory of hydrodynamics with internal degrees of freedom. So this means that what they want to, the hydrodynamics with internal degrees of freedom is a theory which is based on the fact that the stress tensor is antisymmetric in the non-relativistic case. So the Cauchy stress tensor, you include an antisymmetric viscous term. And from the kinetic theory point of view, they were not able to reach this antisymmetric stress tensor simply by the equations of motion. So they had introduced by hand. So they wanted to match these two things.
No, I understand, but my question was more general. To derive a Barnett effect, is it a must that you have an antisymmetric part of the energy momentum tensor?
In principle, if you need to, so if you want to discuss it in equilibrium, you don't need to. I mean, in the sense that if you have a statistical operator, like as we will see, also in the case of relativistic system, even in absence of the spin tensor, we can have a polarization actually in equilibrium.
Okay.
So in general, actually, in general case in relativistic systems, you don't need to have a spin tensor to describe a spin polarized fluid, as we will see later. Anyways.
Okay, thanks.
So, okay, so the canonical currents, okay, here I mean canonical currents. So this is something that, I mean, how do we normally derive energy momentum and spin tensor? It's from the assume, I mean, we enforce like Poincare symmetry in our Lagrangian, then we apply the Nether's theorem, then we get the conservation laws. So the energy momentum conservation will give rise to the conservation of the energy momentum tensor, and the total angular moment. And when we enforce invariance of the Lagrangian under 4 rotations, then we have the conservation of the total angular momentum. And this is the canonical spin tensor, this with 3 indices, in which one can somehow naively decompose this as an orbital and the spin part. Here I put the quotation marks because, as we will see in a moment, this definition is ambiguous. And so the conservation law for the angular momentum tensor then reduces to a so-called non-conservation law for the spin tensor. So if there is an antisymmetric part, like normally the canonical tensor has an antisymmetric part, then the spin tensor is non-conserved. It's not conserved. So the reason why this definition is ambiguous is that because we can always define new tensors such that the global charges, namely the total energy momentum and the total angular momentum, are left invariant, are conserved when we apply these transformations here, which are named pseudo-gauge transformations. And so that's why it's not so straightforward to identify orbital and spin angular momentum, as I was saying before. Also, in the case of the canonical currents, there is a further sort of problem, namely that the spin tensor is not even covariant, as we will see in a moment. However, this transformation is pseudo-gauge transformation. It's important, of course, to know that they leave the total angular momentum invariant, but they modify the orbital and the spin part, also the global orbit and the global speed part, defining this form here. So there is one sort of extreme cases of these pseudo-gauge transformations, which are the Belinfante case, in which the spin tensor is zero, as we usually define the Belinfante's case. In the case of the canonical free Dirac theory, these are the form. Here I will go quickly through this. And so the global spin, as I mentioned, is actually a non-covariant object because the spin tensor is not conserved. You can actually prove that once you integrate over the hypersurface, the integrand is not conserved, and actually the quantity, the integral, it doesn't transform as a tensor. And one can actually see it from this form, which somehow it is given by the straightforward to see also the reduction to the non-relativistic case. But the problem is that when you apply in one particle state to this object, it will give the spin in the rest frame, no matter the frame of the particle. So, somehow there are a lot of discussion in the literature, but since decades and decades, and there are some ways also to define new currents such that the new global spin is a conserved, is transforms properly like as a tensor.
The interruption. Can I ask a naive question?
Yes.
In the previous slide, you said that S mu nu C does not transform as a tensor. Sorry, the next slide.
Yeah.
So S mu nu C does not transform as a tensor because it does not. It is not conserved. But
yes,
why it is the case? The right-hand side of the second equation in your slide would be looks like the tensor. Why?
Yeah, it looks because only for the indices, but if you calculate, it's not. And indeed, the conserved, for example, if you take the integral of the hypersurface, you will see that it depends on the hypersurface. You can prove that. So this means that it's not conserved. This means that it doesn't transform as a tensor, because when you calculate the integral on hypersurface in time later, then it's not the same. So you can
Enrico,
prove.
sorry,
Yeah?
but I completely don't understand. You have defined, canonical spin tensor upstairs, second line. It's a tensor, yeah.
It's a tensor, but it is if you calculate the 0,0 component, for example, it's zero in any frame. So,
but somehow if you have a tensor and contracted with the element of the
but here, what I mean is the 0,0 component. But then you have to integrate. The fact that you are integrating doesn't make this a tensor, and this you can prove mathematically. Unfortunately, I didn't put the backup slide here, but I can show this.
I suggested that we put all those comments to the end of the talk. Or Francesco, do you have a very quick comment? Francesco, do you have a quick comment?
We can postpone it. We can postpone it at the end, right?
Yeah.
Yes.
But,
okay.
Okay. So I go further. Okay. So then this problem was somehow one of the solutions to this problem was found by these two gentlemen here, Hilgevoord-Wouthuysen, in which they proposed to derive the Nether's current from the Klein-Gordon Lagrangian, and they managed to found a conservation spin tensor which is conserved, and an associated global spin which is a tensor. So it's compatible with the Frankel condition, and the superpotential, these unknown quantities for the pseudo-gauge transformations are given here. So this is just to show that it's possible to, of course, define a proper conserved tensor, at least for free fields. So there are other choices here. I just go quickly here. There is the choice from the book by the Groth, Van Loo, and Van Werd. And also one can actually derive it from another Klein-Gordon Lagrangian with second-order derivatives. Just to mention that one can play with these objects. And so let's go back to our how to apply this in polarization or in polarization heavy ion collisions. So our point is to calculate the spin polarization for particles emitted by our Coulomb plasma, or our somehow thermal medium, and the operator. So this is the formula, the basic formula given originally by Francesco, and so one can show that this is something, since it involves the total charge, it's something that's the expression is a pseudo-gauge invariant. However, now the problem is that we want to find an expectation value on a thermal state. So the question is, does this imply a new somehow degrees of freedom of the pseudo-gauge transformation, in the sense that does the thermal average imply something regarding pseudo-gauge transformation? So how do we understand what is the effect of pseudo-gauge transformation in statistical physics? So one of the most fundamental approaches is the one proposed by Zubarev, is to find the statistical operator through the maximization of the entropy with given constraints on the density and of energy and momentum. So now we have also spin tensor, so we need to enforce also the total angular momentum constraint on the density when we maximize the entropy to find our statistical operator. And so you can prove that the solution of such a procedure is the density operator given by this form here, where now besides the Lagrange multipliers associated to the energy momentum conservation, there are also the Lagrange multipliers associated to the total angular momentum conservation, which we call the spin potential. And as an antisymmetric tensor, because it has to contract with the spin tensor. And this will be the new somehow variables in the game. Let's see, first of all, what happens in global equilibrium if we have, so we started from the canonical, so the canonical as an antisymmetric part. And one can show that the condition for global equilibrium, of course, the condition for global equilibrium are those that are such that the statistical operator is invariant under the upper surface integrations, and then one gets this condition for global equilibrium. So the divergence of the integrand, the divergence of this integrand has to be 0. So one obtains these equations here in this box, and these are the conditions for the Lagrange multipliers to be in a global equilibrium state. So beta is a Killing vector. Its omega is the thermal vorticity, and furthermore, it has to be constant. So now what happens if you want to apply a pseudo-gauge transformation? So we start from the canonical as before, then we go to a new set of tensor that we call with prime through a pseudo-gauge transformation. So we express TC in terms of the new pseudo-gauge transformed currents. And then we see that the conditions such that the new operator, so the one found if we had constrained the entropy with the currents, with the new currents, and the one canonical transformed, the question is, well, when they are the same. So in this case, there is equivalence in the description between one pseudo-gauge and the other. And the conditions happen to be those of global equilibrium, because what we need to do is that these green terms vanishes and these other purple terms vanish. And those are the conditions in this global equilibrium. Therefore, we can say that there is equivalence in the statistical description is equivalent in global equilibrium. So what does this imply? So So the question is, do we necessarily need a spin tensor to describe a polarized system? So the answer is not quite, because if you consider, let's first consider the example of a system. So the cylinder of, we imagine that we can put the spin of the particles and the particles in black and in red respectively, all along one direction. So we know that now the equilibrium solution is a solution where the thermal vorticity is different from 0. So in order for this to this state here in A to go to an equilibrium with rotation, either this equilibrium occurs, so the spin relaxes in a sort of time scale which is very, very short. So somehow we cannot describe this evolution through hydrodynamic description, and therefore a description with only the Belinfante stress energy momentum tensor is totally okay. But if we know, if we indeed want to study the evolution of this in this state which evolves to equilibrium, so it starts to rotate in a hydrodynamic description, we somehow need to make sure, we need to understand whether whether the spin relaxes in a time which is bigger compared to the macroscopic interaction scale. And in this case, we need to evolve this according to, we can evolve this as a hydrodynamic field. And in order to do this, we introduce the spin potential in the hydrodynamic description. So this is, once this has been clarified, we can define our spin hydrodynamics. And spin hydrodynamics means that we introduce the conservation of total angular momentum in the hydrodynamic equations, and our field to be evolved, as I said, are the Lagrange multipliers, beta mu and omega mu nu. And so we need to introduce this, we can introduce these 6 new equations of motion. So how do we derive hydrodynamics? So here I wrote that of course the hydrodynamic field are some sort of expectation value of some quantum operator. So in order to study, yeah.
Can I ask a question before
yeah.
that? Yeah. So here, let me just try make sure that I understand that. So this is in equilibrium. If you define your quantities to be thermal averages like this, these equations still have some kind of ambiguity if I just formally make a transformation like a Belinfante-Rosenfeld transformation.
Of course, yes.
But maybe I misunderstood. In the previous slide, you imposed some conditions to remove this ambiguity.
No, I meant that. So this thermal state doesn't have to be in equilibrium.
Oh, okay.
So
I see. So this is not in equilibrium necessarily.
No,
okay.
no. This actually you can define. I mean, in general, there are distributive quantities, which here, I mean, we don't know how to write in general.
Mm-hmm.
Yes. So no, the statistical operator is in general a non-equilibrium operator.
But in equilibrium, you would say that there is no ambiguity.
In global equilibrium.
In global equilibrium.
The statistical average is the same. This is the moral. The statistical average is the same. Can I? No.
Yeah, thank you.
Sure. So we formulate hydrodynamics, our strategies from the Wigner function, which is defined as the Wigner transform of the two Dirac field here. So from our point is to introduce interaction. So we consider interacting fields, and from the Dirac equation we can find the equations of motion for the Wigner function, which has the equation here in the box. And so the reason why we like to, I mean, we study kinetic theory with the Wigner function is because the Wigner function actually, of course, has values in some sort of phase space, and also follows automatically from the equations of motion. So the equations of motion are automatically some Boltzmann-like equation, which is the one here in green, which somehow is very suited for non-equilibrium description. Also, in presence of the interaction, there is some on-shell modification, as this pink equation here shows. And our strategy is, again, to of course, we are not able to find an exact solution, of course, and we find a solution as a power expansion of the Planck constant, so in powers of h bar. So it's convenient to decompose the Wigner function as with the Clifford algebra. So, and we define the coefficients function f, p, v, a, and s. And the equations of motion for the Wigner function we reduce to equations of motion for the coefficients functions, which I don't write here. But our point is that we focus on the derivation of the vector and the axial vector component, and one can show, and in Nora Wegenan's talk there will be more details. One can show that the solutions are given like this if spin polarization effects are considered of first order in h bar. So we are always considering that the polarization dynamics happens on a quantum level. So this is the moral of this assumption, which is good, I guess. So we think for heavy ion physics. So then one can reduce as a transport equation for this component here, this scalar function that involves the vector part of the Wigner function and the axial vector, the one here in purple. So these are the equations that we would like to write down. So we would like to solve, and so it is also convenient and to enlarge the phase space to include spin degrees of freedom, and one can introduce a sort of classical variable which takes into account this spin dynamics. But this is sort of a trick here. This S is just helps us to write eventually the Boltzmann equation as a scalar Boltzmann equation. So all the dynamics are expressed in this scalar Boltzmann equation here in purple. So that's the advantage to go into this phase-space spin. And we assume we parameterize our distribution function as a quasi-particle approximation. So there is some on-shell modification and our distribution function f. And so we can calculate explicitly the collision term, and including local collisions, and this will be the details. This will be the core of the talks of Nora, and using the method by de Groot and Xinli Sheng about using the method of Kadanoff-Behm approach. So the most important thing is that the condition that we find for the collision kernel to vanish are indeed those of global equilibrium. So this is what we found in our calculation, and at the moment we take it as our result, and let's see how we can use this result. So let's say that we want to formulate now our macroscopic quantities in terms of the Wigner function, and we select the canonical pseudo-gauge. So we start with the canonical case. So from these equations here, from this equation here, V mu and A mu that can be canonically in the same way calculated, we can write from the kinetic theory, we can write down the expression for the canonical currents. So the energy momentum canonical, this equation here, and the spin tensor canonical, which is this one. Here again, here the tensor, the canonical tensor, is a first order in h bar. The spin tensor, in principle, this is valid at any order, but we can of course perform an expansion here as well. And this is what we do when we calculate the equations of motion. So if we take the partial derivative of the energy momentum on the spin tensor, we obtain our hydrodynamic equations of motion, and we see the connection with the kinetic theory, namely with the collision kernels and the distribution functions. So we see that the conservation of the energy momentum makes sense in the sense that it's related to some collisional invariant, so which is the particle for momentum. However, when we try to understand what kind of collisional invariant is associated to the spin tensor, we see that there is no such straightforward understanding, in the sense that the general picture would be that if you want to identify the spin tensor as a sort of a spin density, and in global equilibrium, the spin exchange will stop because we are now in global equilibrium. And so this equation here will not properly describe this piece of information. So we not have this piece of information because it will be different from zero even in global equilibrium. This means that the spin tensor, if you use the canonical and our scheme, will not be conserved even in global equilibrium. And this is something that would then somehow respect the physical picture. So if we now calculate this canonical currents in the HW in this Hilgevoord-Wouthuysen pseudo-gauge, so we perform the pseudo-gauge, but now we need to remember that the fields are interacting fields. So so we can modify the pseudo-gauge transformation by introducing a term which takes into account of interactions, such that eventually the currents will look like this one's here. So the T mu nu HW, energy momentum HW, and the spin tensor HW. So we see one thing. So this term here, this Q here, makes such that the new spin tensor has the same form as the non-interacting spin tensor. Of course, the fields inside will be interacting fields. But in the energy momentum tensor, there is one interesting feature that we acquire an antisymmetric part only due to interactions. So the HW tensor, an energy momentum tensor, for free fields is symmetric. However, here in this construction, it will acquire an antisymmetric part due to interactions. And this will be something that we would like to enforce in our hydrodynamic equations, and now see what happens if we now go calculate the equations of motion through the kinetic theory. So if we again substitute the solution for the Wigner function that we found, we obtain that the energy momentum tensor at first order in H bar is actually the same as the canonical, as given by the usual energy momentum tensor. However, the spin tensor is different, and we can apply the conservation laws and the Boltzmann equation that we have derived, and so that we can express the equations of motion in terms of the collision kernel. And we see that the conservation of energy momentum is still associated to the collisional invariant energy momentum, and the conservation of spin tensor is associated to these tensors, to the dipole moment tensor. I forgot to write the dipole moment tensor here. I apologize for that. But the dipole moment tensor is that quantity which is conserved in local collisions. So in local collisions, orbital and spin angular momentum, or local collisions between particles, orbital and spin angular momentum are conserved separately. And in case of local collisions, the dipole moment tensor here is conserved. And therefore, the spin tensor is conserved in local collisions. So because sigma mu nu is a collisional invariant. And in global equilibrium also, we obtain again that the spin tensor is conserved, but because the collision term is 0. However, in general, away from equilibrium, with no local collisions, the spin tensor is not conserved, and this implies a conversion between orbital and spin angular momentum. And this would describe the system of a polarized fluid which gets polarized through rotation through non-local collisions. So this is just a little a connection to what is known in the non-relativistic limit. So we don't want to make a connection to formal, but the point is that we can take the non-relativistic limit of these equations here, of these equations of motion here. And what we obtain if we take the non-relativistic limit is this form for the stress tensor in here. So this is also the form that Hess and Waldman obtained of their non-relativistic theory, but they introduce a phenomenological quantities to mimic the effect of such conversions. In our case, this is all automatically taken into account from, say, first principles. And this also can be cast in a form of hydrodynamic equations for the so-called micropolar fluids. So micropolar fluids are those fluids which indeed don't even need to be quantum, which are made of viscous fluids, which are made of particles with some internal angular momentum. So some internal degrees of freedom of angular momentum, which can be, for example, also for classical particles, like for little rigid bodies. So the particles of the viscous fluid are little rigid bodies. And they have some non-conservation law of the internal angular momentum. So in our case, so this green L here is the internal angular momentum. The C is the so-called coupled stress tensor, and the T is the stress tensor. So we can make a connection between our non-relativistic limit and this theory of non-relativistic fluid with internal angular momentum degrees of freedom. And we can establish a connection between the internal angular momentum and our sort of spin variable, the average over the spin variable. This is an average over the phase space, this here. And the same for this coupled stress tensor. And so here one can see that the physical meaning is that the change of angular momentum, internal angular momentum, is given by the coupled stress tensor and an antisymmetric part of the stress tensor. These have many applications, some of them even in condensed matter, in spintronics, in which somehow they were used, these equations were used to study spin transport in spin fluids. So they are sort of well established, these equations of motion here. And so now we can come back and discuss the polarization observable in heavy ion. So this is basically our moral. So we can so in heavy ion, in the relativistic case, the particle polarization operator is gauge invariant by definition. Then the thermal, when we take the thermal average, is in general pseudo-gauge dependent. We see that the equivalence is restored in global equilibrium. And so maybe a way to possibly to understand more about the pseudo-gauges is to see from the polarization in heavy ion, to study non-equilibrium effect in heavy ion, and to see in principle which kind of pseudo-gauge is more compatible with experimental data, and so this implies also that one would like to have a hydrodynamic evolution for the to calculate the spin tensor. So with also spin degrees of freedom are included. So this is just final remark, which is separated from what, I mean, it's not related to heavy ion, but just to show you something more about the pseudo-gauges. So there can be a connection between the ambiguity of the relativistic center of inertia and the global spin actually can be established. So we know that in relativistic systems, the center of inertia doesn't have an ambiguous definition. However, one can connect the different definitions of the center of inertia with different definition of internal degrees of freedom, like spin, which in the quantum case are spin. Here, just to mention that the message is that in the massless case, we have the side jump because there is no covariant definition for Q mu, and on the other hand, for the massive case, there is, and this actually coincide with the HW definition for the internal degrees of freedom. So here we have a connection between this HW pseudo-gauge and something else, some other information about other system. Also, there is spin tensor is also something which is discussed in the Einstein-Cantor theory, and we also had the talk by Umut this week, in which in the Einstein-Cantor theory, in presence of torsion, one can actually define the spin tensors through the variation with of the action with the spin connection. Therefore, there is always this. So in conventional general relativity, Beninfante, normally one associates the energy momentum tensor to the Beninfante. In the Einstein-Cantor theory, is also appropriate to define it to introduce antisymmetric energy momentum tensor in general. Anyways, this just to show some connection of pseudo-gauges with some other field. So in conclusion, I discussed the invariance of physics somehow and with pseudo-gauge transformations. So when pseudo-gauge transformation may play a role, and we saw that statistical average, in principle, in global equilibrium, the equivalence is restored, and in hydrodynamics, we saw that the HW pseudo-gauge seems suitable to describe the orbital-to-spin angular momentum conversion. And also in the future, of course, the next steps will be to derive spin hydrodynamics, dissipative spin hydrodynamics, and to study non-equilibrium effect, as I mentioned, and maybe this can be some sort of explanation, can help us understand more about the spin design problem. Thank you.
Thank you, Enrico. Thank you for the very interesting talk. So now we have time for discussion. Yeah. Oleg, yes, please.
Thank you, Enrico, for a very interesting talk. And actually, well, I have several questions, but I would select the one. Okay. How essential is for your derivation that spin tensor is totally antisymmetric, not only with respect to interchange of two indices, but totally antisymmetric, so its dual is axial current?
Yeah, the thing is that we don't want that actually. So so in the case of the canonical for Dirac case, that's the case, right? So it's totally antisymmetric.
Exactly. You don't use the antisymmetry in your
not the total antisymmetric. We go from the canonical, which is spin tensor with the all totally antisymmetric indices, but we go to this Hilgevoord-Wouthuysen, so this HW, which was proposed in the 60s. So in that case, it's not totally antisymmetric.
Well, may I also ask the question which I was already asking last week? You didn't take into account any boundary effects?
What do you mean boundary?
Well, actually, Well, to preserve the total conserved charge.
Yeah. Absolutely. I mean, the thing is that the total charges is of course ensured. So here,
I mean that the possible source of difference between the Belinfante and canonical can be also the boundary or surface effects, and in this case, I mean just physically, the source of spin orbital coupling can be also located at the boundary.
Yeah. So this is actually, I think it's automatic that in this case we reshuffle the density such that we may have something that when you integrate goes away because you're interested in the total charge, but when you stick to the density, it doesn't. So I think yes. So we have different densities, which anyways, when you take the total integral, they go to zero. The different parts.
So this is assumed, right? So
yes. This is always. This is not. I mean, it's not only assumed. This is ensured by these transformations. So.
Well, okay, thanks.
Okay, Francesco. Yeah.
Can you hear me?
Yes.
No, I just had a comment about this. Okay, so you are in the right slide. Okay. So there was some discussion earlier about this S mu C, whether it is a tensor or not.
Yeah.
So I want just to point out that the S lambda mu C, so the rank 3, this is a tensor. When you integrate it, it is a tensor only if the hypersurface is fixed.
Yeah, this is not what we would like.
That is maybe a reconciliation between Wojtek's remark and Masaru's remark. So it is true that it is not a tensor if it is integrated over arbitrary hypersurface, because S lambda mu C is not conserved. It is formally a tensor if the hypersurface is fixed once forever, once for all observers.
Yeah, but this is not what we would like, right? Because the covariance is exactly that we can change the reference.
No, I think I disagree somewhat.
No.
I disagree somewhat. It's like the temperature, you know, if
formally it is a tensor.
It's a tensor, you know, it's defined like temperature is defined in the local rest frame of the fluid element, and you choose some special thing and it's a scalar, you know, temperature.
No, that is it is true that is that no, I mean that if you change the frame.
Yeah, it's not the same.
No, if you change the frame and the hypersurface is kept constant.
It's a tensor, but you know, in the definition of this tensor, there is a definition of the hypersurface, but it's a tensor, you know.
I will show you privately what I mean.
No, it's a tensor. It's a tensor, you know. It's
no, I mean
independent
no, Wojtek, no.
Of course it is.
You can prove it that it's not.
No, you just
I completely failed my remark. I was trying to reconcile both. I completely failed.
No, I think that I understand what you mean, and somehow because I think
so it's not a tensor in the sense. I mean, in the quantum field theory books, you always find that this cannot. So that the integral of a conserved, the integral of a non-conserved current cannot be a tensor. It is a tensor. Formally, it is if you keep the hypersurface fixed.
Right. Right.
Okay.
Yeah, but
I hope that I have reconciled the
yes.
Then I have
ask
a question.
But this means that d sigma is also a vector. It should be transformed, and if it is properly transformed,
and it doesn't.
Then it's a tensor, right?
It doesn't, because this doesn't transform as a tensor when you take
it transforms. You know, I think I agree with Francesco. I think you want to have more than a tensor. You want to have this definition which is independent of d sigma. Yeah,
but it's okay. It's related.
Sorry, may I say something? So I think it depends how you choose your d sigma lambda. So if you choose to d sigma lambda in one frame and make it a vector, so make a covariant transformation to another frame, it's covariant. But if you keep your d sigma lambda so if we choose, for instance, your d sigma lambda, like having only a time component in any frame, There's only covariant.
I agree, but it's a different story, you know. This sigma is, you know, is one form, is a tensor. Contracted with other tensor is a tensor, you know. You want to have more, you know, than this.
This is what we mean. I mean,
yeah, is a tensor.
Yes, maybe.
Okay, this is maybe a problem of definitions.
Yeah. Okay. Shu, do you have a question?
Yes. Sorry for asking something else. So thanks for a very interesting talk. So I'm just wondering if you could expand on this difference between local collision and non-local collision. Did you derive it in some specific theory?
Yeah, so we derived, this would be the details also. I didn't give the details here, but will be given by Nora and Shili. Yeah, in the sense, we follow two approaches to calculate the collision term, but both of them are based on the gradient expansion, our H bar gradient expansion. So non-local collisions are considered on the same level as H bar expansion, because the locals will go with some derivative, and therefore they are on the same order of H bar expansion. So that's why for a complete analysis for the collision term, one needs to keep at first order both the non-locality and the usual solution of the first order of the Wigner function. But I don't know if that answers your question, but I mean, the model is using by the book by the Grottis, which is basically done by computing the expectation value of, for example, the collision term, which looks like this, by introducing completeness of in and out states, so in and out states, and in the case of Xinli, we'll talk about how to derive this using the Kadanoff-Bain approach. So
now
we use a general interaction. We didn't put it explicitly in the interaction here.
So non-local carries gradient, and both local and non-local are first order in H bar.
So local can have first order in H bar as well. Yes, zeroth order in H bar local can only be local. That's
Okay, I see. Thank you.
Sure. Okay, Wojtek, do you have another comment?
Okay, I have hundreds of questions, but first, I think it's very attractive what you did. I think because you have really connection between vorticity and polarization. So there is, I think, great achievement. So I simply envy you that you can just figure it out how to do it. But on the other hand, I have many doubts. For instance, you are always saying that all those spin effects start with H bar squared.
With H bar. Yeah.
Yeah, but in fact, the spin tensor starts with H bar. So I think your function of, for instance, axial component starts with H bar.
No,
in our case, I think what we are doing somehow it starts, you know, with H to the power 0, and somehow in old days in 80s, people were deriving also the equations for the spin evolution in the electromagnetic fields, you know, so it's possible to derive this BMT equation for the spin evolution, and then in electromagnetic fields, you know, and then I think that the expansion starts one order of magnitude earlier than you do. So somehow, so I'm not convinced really that we have to start with the order you.
No, we don't have to. The thing is that we made this assumption because first, it's something reasonable for heavy ion, because we can somehow at least think that the conversion. So there is no macroscopic polarization at the beginning. Let's put it in this sense. So there is only quantum effects. Second, in the spin tensor, so our expansion is connected to the gradients. The H bar in the spin tensor, which I think you are referring to this, I guess.
Right.
this one is there even without gradient. So this is an overall. So this will not enter the h-bar gradient expansion. So it just tells you that the spin tensor in the Dirac case goes with an h-bar. This is what it tells you. I think that's it.
I think that all spin tensors are equivalent in some sense.
Sorry, there was some lags. Sorry, can you repeat?
I think that all, energy momentum tensor and spin tensor are really allowed, because somehow if you prefer to use, one option, I think the other remain in the theory. It's not like this. This is the point emphasized by Leonardo, that somehow if you go to Bell-Infante, I think the equations for the, canonical forms, they are still valid in the theory. They are present. It doesn't mean that if you prefer some form, then the other are somehow wrong. No, they are still valid,
True.
So I think that one has to combine somehow observables with one choice of.
That's exactly.
Like choosing the gauge. You have to choose some gauge to do the calculations. You connect observables with some, mathematical expression in one gauge, and then you do the calculations.
But there is one. So the thing is that still the localization of spin density is different. So you want to somehow change the spin density.
Yes, so I think localization is not physical. I think it's like
we may argue about this. We may argue about this because there are people in optics, even though that they do classical also with classical radiations, who tell you that they can somehow distinguish between an orbital sort of density, spin density rather than another, due to the experiments that they do and so on. So there's some more other discussion.
Okay.
Just as a comment, which I think is...
okay, can I finish? Sorry, one thing about Wojtek. The only thing is that our thing just is related to the connection with kinetic theory. So in the connection with kinetic theory, this seems reasonable to use this one here. But so yes, sure, please, Giorgio.
In optics, I've looked at these papers, and there is also parallel in spin, deep inelastic scattering type stuff. They can, but the price at which they can do it is by having a preferred frame of reference.
I know, the laboratory frame, yes, of course.
And in your case, your approach, because you have conservation of particle number in your kinetics, right?
Yeah.
I think that this allows you to somehow reproduce a preferred frame. If you have a conserved number of particles, then you can go into a frame of each.
Oops, Giorgio? Hello?
Giorgio?
Possibilities is associated with the approximation.
There was some hole in your discussion because the connection.
Giorgio, you were disconnected.
My internet, I have a question though. Your global equilibrium, if your global equilibrium is independent of pseudo-gauge transformations, and it does because you have the Zubarov operator, and your local equilibrium depends on it, does it mean that your kinetic theory doesn't reach global equilibrium if you wait long enough, or what?
Why no? It means simply that maybe the distribution functions are actually depend in turn on the pseudo-gauge, but eventually in global equilibrium they reach it. So the global equilibrium state is a state for each pseudo-gauge. So I think
So when you wait long enough, pseudo-gauge independence goes away.
Yeah, I think so. Yeah, this is the model, yes.
Okay.
Okay. Umut.
Yeah, hi. So I was just, it's a very short question. Don't worry about in terms of time. So just trying to make a conclusion that if you include the non-local effects, do you, in the end, so if you perform all the calculations for quark-Coulomb plasma, what is the reason to believe that this would change, for example, the sign, your original motivation?
No, we don't have such a strong reason just for the sign. No, this we cannot tell.
I know. Yeah, but do you have any indication that this would contribute in a...
Not quantitatively, no. We are just somehow trying.
I see, yeah. Okay.
That's the real truth. Yeah.
Okay.
Thanks. Yeah, Francesco?
I would like to make a comment about this. It was mentioned by Enrico. When you compare with non-relativistic physics, one has to be very, very careful, because the spin tensor is inherently a relativistic object. It is quite different from the magnetization tensor, which is degenerate in the non-relativistic limit. In other words, when you have, and it was pointed out by Enrico in the talk, or maybe not emphasized, but it was
not enough.
That when you have a relativistic system, you only have particles, and therefore the magnetization tensor, which can be, say, loosely speaking, approximated by the number of, say, the spin of particles minus the spin of antiparticles, is different from the spin tensor, which is a charge conjugation even, and it is the spin of particles plus the spin of antiparticles. These two tensors in the non-relativistic limit are the same, because you only have particles. Therefore, when, say, assessing the role of a spin tensor with non-relativistic physics, one has to be extremely careful because of this degeneracy. The spin tensor is something which is typical of a relativistic system, and we are really discussing whether it is needed in a relativistic fluid, because only in a relativistic fluid you may have configurations where particles and antiparticles have the same spin.
Okay, thank you for the comment. I think we should put a lot of discussion to the roundtable discussion session about like the pseudo-gauge, the rule of the pseudo-gauge, and the covariance of the spin tensor. So now, Nora, do you have a quick question?
I just want to answer to Wojciech's question about the spin at the zeroth order. So I think the difference is if you have local or non-local collisions, because I think it's consistent like you do it and also consistent like we do it. Because if you have local collisions, your spin is a collision invariant. So you can have a zeroth order polarization which survives at equilibrium. But on the other hand, if you have non-local collisions and the spin is not a collision invariant, I think any polarization of zeroth order will dissipate when you reach local or global equilibrium. I think that's the difference.
Yeah, but would you agree that if there must be some parameter for these non-local effects, and if you switch them off somehow, one should get what we have,
Yes, I agree. Yeah. If you have local collisions, I agree.
Okay, so there's at least I'm relaxed.
Yeah. No. The thing, of course, what you do doesn't contradict. We don't contradict what you do. This is not our point.
Okay.
Yeah, okay, good. So we really have a lot of discussion, but it seems we really should continue the discussion in the roundtable discussion. So remember, we will have a roundtable discussion today. So let's thank Enrico again for this very interesting